All right. So for today's lecture, we have, as Paulo mentioned just now, a review of some related areas that we will be using during the rest of the course. It's really related to a lot of underpinnings of the models that we'll be studying in the class. So first, a very brief introduction on the need to address uncertainty. It's a few obvious things, but it's a good introduction to make. Then we'll see 4 probabilistic graphical models. Typically, you'll see these in the literature abbreviated as PGMs. So these are the 4 main ones, and we'll see that they are quite related amongst themselves. So the first is Bayesian networks, very well-known model. Then Markov random fields, which are the underlying model under Markov logic or Markov logic networks. And the last of the 4 is Markov chains, which is also a quite related model that is also at the basis of many approximation algorithms like MCMC methods. And at the end, we'll see a little bit about probabilistic soft logic that we'll be hearing more about in the course, because there's a neural variant of this already. So as I promised, the need to address uncertainty. In general, we don't even have to talk about AI, artificial intelligence. We need to see that data management is at the core of many of these applications, related to intelligent systems. You don't even need to get to the point where you're implementing any really smart stuff, but just doing good data management already runs you into a lot of issues. Some examples of this is natural, or what you could call inherent uncertainty, where some domains are, you could say, in nature, inherent, such as weather forecasting, financial markets, that kind of thing. Why do I put the scare quotes there? Because a lot of this stuff is quite philosophical. If you start studying, the real roots of reasoning under uncertainty, you'll run into a lot of things that you have to, study from a point of view of epistemic philosophy. So the second kind is uncertainty arising from automated processing. This is more mundane, right? If you have like data integration, assume that you take 2 or more databases after some companies merge, you'll have a lot of things to take care of, right? Like data cleaning, like schema mapping, that kind of thing. And of course, you won't be able to know exactly how things match, right? Maybe some of the columns are named address, and the other one is, city and postcode and stuff like that, or they're separated into several different fields, and one just says address that has everything all together. In that case, there's a lot of processing there to map one into the other, and you could make mistakes, or you might not even know for sure. And then the other one is uncertainty arising from inconsistency so both things can happen at once in the same data set: inconsistency and incompleteness. Inconsistency typically is referred to also as overspecification. It means that you have, for instance, for the same student in the same class, you have 2 different grades, and that's something that can never happen, right? And underspecification or incompleteness would be for some student and class, you don't even have a grade. You have like a missing value there. So as I said, both things can happen at once. So all of these are sources of uncertainty that you have to deal with. Another way of looking at these sources that is proposed by Russell and Norvig is one of 3 things. It could either be, they're related to what I just said. So the first is called laziness. It's just very difficult to get things right, and so you just decide that you're going to implement these things as uncertain. But it's not because they are, it's just because you don't want to, or you can't, with the tools that you have, model things perfect. The second is theoretical ignorance, where there's just not enough information to model a domain. You have to deal with, this is quite related to the one that I called the inherent. And that's where it gets philosophical. Is it the fact that I don't have enough, don't know where every air molecule is at every given point, and if I did, could I model the weather without any uncertainty? That's a really interesting question. The third one is practical ignorance. Even theoretically, you have all the necessary knowledge. Maybe for specific data points, you have information that's missing. For instance, in some medical application, for instance, you might understand everything very well in order to make some sort of diagnosis with the patient, but you don't have the lab tests aren't done yet, so you don't have the data available for this patient in order to make a prediction. So that would be practical ignorance. So in this class, we're going to see the most important, the most successful approach, arguably, to address these kinds of scenarios, which is the probabilistic approach. There are other kinds. We'll see a little bit about these possibilistic or fuzzy values at the end with probabilistic soft logic. But there are other kinds of models. They're less well known, and in some cases they are very well suited. But in general, when you reason with uncertainty, there is some probability under there. And another philosophical thing, and I promise that's the last one. Probabilities are typically interpreted in one of two ways, and sometimes people just don't even say, right? It's either obvious or it's just, it could go either way. The first one is frequentist, or also called objective, again in quotes, because this camp says that probabilities are tied to experience. You can't talk about probabilities without saying, well, this is, I can tell you that there's a 55% chance of this because I have all this historic data, and the rate at which this happened is 55%. Whereas the Bayesian or the subjective camp says that probability is just a matter of some opinion, right? An expert can just come along and say, yeah, I gather it's probably around 55, and that's enough. It has to follow, of course, the axioms of probability. You can't have the expert say the probability of the event is 55 and the probability of the complement is not 45. So there are things that have to hold, but where they get this number is a subjective matter, right? So on to the matter at hand. Probabilistic graphical models, they're called in this way because they are based on graphs, the mathematical structures that you have probably encountered many times in your careers. And they are used to represent knowledge, like we've been talking about an uncertain domain. So typically, we'll see that all of them, the ones at least that we see in this class, and all graphical models in general, will follow the following template, where nodes denote random variables. They can typically either be discrete or continuous distributions. And edges can also be either directed or undirected. We'll see both kinds in this class. And the edges encode some kind of probabilistic dependency between the two variables that are joined by the edge. And the lack of an edge will denote some kind of conditional independence. So you'll see that in both cases I said some kind. So some kind of probabilistic dependency and some kind of conditional independence. That's where the richness of all these different models comes in. And of course, the tractability of the underlying algorithms that we'll have to use in order to get any kind of interesting result from them. So as I mentioned, these are the four kinds that we will cover in this class. And for ease of presentation, the formulas, they are, as you will see, some of them are more involved than others, but we will focus on discrete models. So where we have a finite number of different possible values, but there are continuous versions of each of them as well, and we'll see some of them at the end with PSL.